Hello, welcome to Convergent Dialogues. This is Xavier Bonilla. On this episode, I am very happy to have Neil Shubin back on the podcast. Neil is a paleontologist and evolutionary biologist. He's also a professor at the University of Chicago and Dean of Academic Strategy for Biological Sciences Division. He has a lab. He does lots of wonderful research. As we kind of mentioned in the conversation, he's most known for him and his team for the discovery of the 375 million year old Tiktaalik fossil, an intermediary species between fish and land animal. And he is the author of many books. We talked about some of his previous books when he was on here before. But he's got a new one out, and that one is Ends of the Earth, Journeys to the Polar Regions in Search of Life, the Cosmos, and Our Future. And that's the book that we discuss in this conversation. We start by talking about polar science, what it is, how it's so important for understanding life in the past, how we got to where we're at now and where we could be going. We talk about the Arctic up in the north and the continent of Antarctica and how there's some differences there. There's also some similarities. We talk about hot ice, blue ice, life under the Antarctic ice, and how under the ice in Antarctica there are lakes, many, many lakes, very large ones. There's land, there are mountains. Very, very fascinating. We talk about some of the fossil discoveries that have been made down there, meteorites that have crashed into Antarctica, the impact of climate change, and many other topics. As I said in the conversation, the book kind of feels like almost like a novel. It's like we get in his backpack and we just go along with him to the Arctic and Antarctica, places I haven't been to, a lot of people haven't been to. So it's really, really wonderful to kind of get in through his eyes and see what it's like and how things have been. Some of the other wonderful explorers and scientists that have been there for 60, 70 years. So it's all very, very exciting stuff. Of course, you can find this conversation and all other conversations at convergingdialogues.substack.com. Also on YouTube, like, subscribe, share with your friends, contribute. All of that's much appreciated. And now I bring you Neil Shubin. I'm here with Neil Shubin once again. Neil, thanks so much for coming back on the podcast. I'm delighted.
Oh, it's great to be here. Thank you for having me.
Oh, yeah, for sure. You got another book out. It's called Ends of the Earth, Journeys to the Polar Regions in Search of Life, the Cosmos, and Our Future. And I'm pretty sure I read this in one sitting. It was
really? Wow.
It was really good. I just sat down one afternoon, and I finished it on the second sitting, but I was like, I know you're writing stuff and it's obviously very good, but first, half, 2/3 of the book it almost felt like a novel in some sort. It was just really good. I was really into it. I was like, wow, this is super cool. So I'm excited to talk to you about it. Before we do, just remind listeners kind of who you are, what your day job is, and all the things that you're into.
Yeah, my name's Neil Shubin. I'm an evolutionary biologist. My day job is I'm a professor at the University of Chicago, where I run a laboratory that studies fossils and DNA. We do expeditions around the world. And I've had the great privilege to work in polar regions, the Arctic and Antarctica for, almost 4 decades now.
Wow.
And so that's how that book was born, essentially.
Wow. Yeah, it's super cool. So, obviously, you've had some great discoveries. You've written some great books. I think Our Inner Fish was great. I love that one. And so this one was super cool. I was kind of taken aback. I was like, wow, I never really realized it. You don't hear, what is it, right? Scientists are the ones that mostly go to Antarctica. You don't hear a lot about Antarctica or the up north. So it was cool to kind of follow you around in your backpack, so to speak, in the book. That's kind of how it feels. And so, I guess just a general question here. How much has polar science become pretty important over the past 70 plus years for understanding Earth's history, right? We have all these things that we know about the planet and things we're still learning, of course, but how much has polar science become pretty instructive?
It changes the way we see the world, honestly, and that's the spirit of the book. Polar research has changed the way I see the world, how I see the planet, how I see life and how it evolves and how it responds, how we're tethered to the planet as a species, how we're
Mm,
connected to the planet,
mm,
and how
mm,
changes to the planet have guided our evolution and will guide our future. You work there, it changes how you think about yourself. You learn all kinds of things. Living in a tent, nylon tent, at minus 20 degrees. I mean,
That's wild.
not all of it's pretty.
Hmm.
And so there's a lot of lessons here. And you learn about the workings of the planet. You learn about
Mm,
the workings of life, um, and these are really special and fragile places.
mm,
And when you work in these regions, you cannot fail to be affected by them in a really big way.
mm. I can imagine. So, I mean, I've traveled a little bit, but the goal is always to get to all seven continents and get to Antarctica.
It's a good
How
one.
how you can tell us some things, I guess, to do there of sorts, but how much, I guess, training is involved? I mean, you don't just kind of hop on a plane and you get your sandals and or your boots or your whatever. You kind of there's some training, especially for you doing excavations and stuff. How do you? Yeah, what's the training? Is it all kind of like in vivo on the ground, or do you do a lot of stuff in the ramp up to it? How do you it's terrible, wind conditions, ice, snow, very
Oh yeah.
cold, minus 30, 40 degrees. How do you train for that?
You're like, put it this way. You can be hundreds of miles from the nearest people. You could be living for 4 to 8 weeks in nylon tents, really remote in remote conditions, which are dry, stormy, sometimes sub-zero temperatures. You have fauna that can pose a threat, whether they're polar bears or whatever else. So these are landscapes where if you want to lead an expedition, particularly a scientific one, it takes about a year or two of planning before you even step foot on the ground.
Wow.
So planning the meals, planning the food, planning the crew, planning the gear, planning, and planning and planning. Everything, every little thing gets planned. Now, the thing about it is what controls the show there are not your plans, it's the environment. So as soon as
Mm,
you appear on the landscape, everything can change, right? Because the
mhm,
weather and the logistics. But there's a lot of preparation from the food to one's own body.
mm,
I mean, one has to be in decent shape to work there.
mhm,
Prep in that way, prep mentally for it in a lot of ways, because it can be mentally very challenging working there. Not just because of the conditions, because
mm,
imagine you're going 3 to 4 weeks not finding anything.
mm,
And that mental piece is a big deal. And so, yeah, a lot of planning when you're on the ground.
mm,
A lot of working with the crew before we leave in terms of their gear, in terms of their mental attitude, in terms of their scientific preparation. Yeah, so
mm,
planning, planning, planning.
mm. Yeah, I had to imagine that a lot of it is kind of risk management too. You have to think about or plan all the things that could go wrong. Because if you're
Oh, yeah.
there for weeks and weeks and weeks, there's no people around. You're like, okay, if this happens, okay, what do we do? If this happens, what do we do? I mean, it has to be, again, mentally, it has to also be stressful as well, no?
Yeah, I mean, I think the kind of the thing about planning is it makes it less stressful, and so
Okay,
the
there you go.
better
Yeah.
you plan, the
Mhm.
less of an adventure it is, right? So we have a saying is if you had a big adventure, you didn't plan right. It's
Mhm.
like we kind of like to keep it between the lines. Now nature has a say in that. Storms
Mhm.
will come through and wipe out camp. You
Mhm.
have things that happen. There are challenges with aircraft and people get injured and so forth. But we try to minimize that as much as possible. Um, but you do your best on this
Sure.
planning. But the key thing, what the planning really does is it's like what did Eisenhower say about warfare? He says plans are essential, but plans are useless.
Uh-huh, yeah,
I
that's
mean, you
right.
need the planning, but no enemy survive. No combatant survives contact with the enemy. I mean,
Mhm.
no plan survives contact with the enemy, I should say. And
Mhm.
so the plans are there as a guide because once you're there, the Arctic or Antarctica has a say in it.
Yeah, yeah, I can imagine. So tell us, I guess, just the difference. I mean, there's Antarctica, right, which is the southern part of the globe, and then there's the North Arctic pole. And so you mentioned Antarctica is icier. I guess tell us. I guess is there technically a South Pole? There isn't, right? I mean, you have the
Oh yeah,
Arctic, which
no,
is the
there's
North
South
Pole,
Pole.
but South Pole. Okay, so
You got
yeah,
both.
tell us. I guess the differences between you've been to both the very top of the planet and the very bottom of the planet, I guess, so to speak. How does it
Right.
work? What's different?
So if you look at Antarctica, if you were to remove all the ice in Antarctica, you'd see land. It's a continent. So the ice, you have
Right.
several miles of ice that lie on top of land. So it's a continent, as we learned in school. Now, the northern part, if you remove all the ice around the North Pole, what you'll see is ocean floor. You'll see sea. So one's a continent and one's not. So there are islands up in the Arctic, but most of it is really, underneath the North Pole, most of it's sea floor. In the Arctic, since you have it's a continent, the ice can be at altitude. So think about this for a second. The South Pole Station, which is a scientific base, sits at the South Pole itself. It sits at almost 10,000 feet. So you have to deal with altitude in Antarctica when you're working on the ice. That's a surprise. So it makes it drier, makes it colder, but also since it's a continent essentially, it's like larger than the continental United States as a block of ice, as several blocks of ice, right? It's cold. So the Antarctica typically, now it can vary based on region, but on average, Antarctica is colder, drier, windier than the Arctic. Now, working in the Arctic, on the other hand, you have a lot of ocean and sea up there. It's much more susceptible to changes in temperature. The ice melts, and a lot happens that way. And it can be wetter when you run a field expedition in the Arctic. So I was up there this past July. You're not in the sub-zero temperatures in summer there as much in the areas we work. You tend to be closer to freezing. And that comes with its own challenges, right? It's like it can be wet, and you don't want to be wet. Being cold is one thing. Being wet and cold is a whole other gig, right? So you have different challenges working in each place. I mean, you have polar bears up in the north. You don't have polar bears in the south. So when you run expeditions, it's pretty funny. I'm used to thinking about polar bears all the time when we're working in the Arctic.
Right.
When we go to the Antarctic, when I first get there, I'm thinking about polar bears all the time, even though there's not one for, 10,000 miles, 15,000 miles, but it's just, I'm conditioned to think that way, but yeah, so different.
I'm still trying to wrap my head around this. So I'm thinking of the globe, and I'm thinking of Antarctica at the, so to speak, bottom, but you're saying there's 10,000 feet of elevation. How does that work? It's like a weird I can't wrap my head around that.
Yeah. So it's land with miles of ice on top of it. And those miles of ice, let me give you an example. So I work on mountains that poke through the ice in Antarctica. They're called the Transantarctic Mountains. So you have the ice sheet, but there are mountains that rise maybe 9,000 feet high, poking through the ice, but you're only seeing a couple thousand feet, right? Because the ice sits at elevation too. So it's like the tip of the iceberg, only it's a mountain. It's pretty remarkable. So the land lies under there, but with thick ice. So we'll have a camp that may be at 5,000, 6,000, 7,000 feet, depending on where we are, on the ice. And then we'll work on these mountains, and we'll climb the tops of these mountains that are poking through the ice during the day. So I work on rocks, not ice. I live on the ice, but I'm there for the rocks because I want to find fossils like, that plushie right there, that kind of thing. And so let me set an image for you. This is kind of what you get when you work there. You're at the top of an Antarctic mountain. Yeah. Okay. You're at, say 8,000 feet in Antarctica. It's cold, windy. You're surrounded by ice. You can follow ice for 1,000 miles in every direction, 500 to 1,000 miles in every direction. Inside the rocks, there's rocks there, are grains that contain fossils of sharks and fish. These were rocks that were formed in ancient rivers and streams. So think about that juxtaposition between present and past. Today we have this icy world. In the past, you have a tropical world in that spot. So working in these regions gives you this image of just how much our planet can change. And then the more you study these regions, the more you realize those changes can happen like not always over millions of years. They can happen really fast. And so that's what working in these places, one of the things these places teach us is that our planet has changed so much over millennia, but our planet is also capable of very dramatic change in shorter timescales.
Can you give, I guess, a sort of, maybe there isn't, right? I have to imagine that being on Antarctica feels probably like another planet of sorts in some regards, but maybe for you it's a little bit different. But I mean, is it anything like other things that we know? So like people that live in maybe northern Canada or Iceland or Greenland or, is there anything like it, or is it very different? Like, is it just so, I mean, ice is ice, but at the same time it's not, right? I guess for other things we know on the planet, is it just like, there's some things that we can kind of connect to, but is it like, no, this is just so different than anything else on the planet?
What makes it different, at least the way we do it as, leading expeditions there,
Hmm.
is we're hundreds of miles from other people. So,
Mm.
we might be a group of 4 to 6 people, but we are separated from the rest of humanity by hundreds of miles, maybe 400 to 500 miles in some cases, right?
Wow.
And the conditions, you'll run into those conditions if you were in, say, the ice cap of Greenland, in the center of the ice cap. Greenland, the center of its ice. You could run into those conditions elsewhere. It gets cold here in Chicago. We get polar vortices where I'm, in the winter. But I'm living in a concrete brick building here in Chicago. I'm not in a nylon tent, hundreds of miles from people. So that really kind of creates a different landscape.
Yeah.
So you have to be self-sufficient. You have to have your have your head in the game. You have to have clear-cut scientific goals. You have to know why you're there, and and kind of know the geology and have done your homework scientifically. So it comes with a whole different feeling and vibe to it when you're leading expeditions to these remote places.
One thing that I'm thinking of here is you're looking for fossils. What do we know, I guess, just briefly, you can just give me the 90-second overview of this, about how old Antarctica is. Most people go to Pangea, right? So, what was it connected to at one point with other places on the Earth where we can see, okay, yes, we see these, you're mentioning sharks and other types of animals that are there and fossilized. Where was it connected? Where do we think that it kind of, how it came to where it is now, but it had a different history, in maybe the Precambrian or the Cambrian, there's a different kind of history there. What's the kind of just very general overview there?
Well, remove the ice from Antarctica and you have the rocks and the mountains, and those can be really ancient. And the Antarctica's moved around over time as during continental drift through plate tectonics. There was a period of time, the late Triassic, about 200 million years ago, even beyond a little bit, where it was connected to Australia and South America and Africa. It was part of the southern landmass. And so we see similar fossils of Triassic or 200 million year old age in these different places. Like there's a fossil plant known as Glossopteris, a little plant. You can find its leaves in the rocks, or fossils of leaves in the rocks. And it's very similar among these different places. So we can tie the geology of Antarctica to the geology of Australia, Africa, South America, and so forth. Now the Arctic's a little different. The Arctic is we work in a place called Ellesmere Island. We've worked in Greenland as well. And a lot of that has moved around a lot more than Antarctica. So what the Arctic rocks I work on in Ellesmere Island today were originally much closer to the equator, 200 to 300 million years ago. So it's moved around quite a bit. But yeah, it's a really remarkable story. And the way we've come to know that is truly amazing. As I tell I love telling the stories of the science in this book. So this book is partially about my experience, but I'm your tour guide, really. Then I turn it over and I tell the stories of the other scientists and explorers. And the way this has been discovered is truly remarkable. People risk their lives to do the science there, which is just incredible.
I do want to come to some of that. It is a kind of global sort of endeavor, and people from different parts of the world. Let's talk a little bit about, I guess, some of the science. You mentioned this part in the book. There's this one chapter where I had a very hard time. Again, it doesn't click with whatever what you think things are. But you mentioned how ice can be hot. I don't explain this. Yeah, explain how it looks in Antarctica with these very low temperatures.
So I was talking to a glaciologist, Sridhar Anand-Krishnan, who's at Penn State, and I was I'd met him in Antarctica. He's a glaciologist, and I talked to him when I was writing the book. And he said to me, he goes, I want you to know one thing about ice. Ice is hot. I'm like, ice is hot. And I took the notes, and obviously it made it into the book. But I thank Sridhar for that. And what he meant by that, and it captures something very powerful about ice. That ice, the melting point of ice, 32 degrees, right? It's kind of close to the temperature of the ambient temperature of most places on Earth. You may have places that get to 100, you may have places that get to 0, but it's in the range there. Now, steel, the melting point of steel is, almost 700 or 800 degrees. So the transition to go from solid to liquid with steel is like nowhere near the ambient temperature. Whereas
Sure.
ice, and water can do that transition, relatively in a small, narrow range of temperatures. So it doesn't take a ton of temperature change to turn ice from, liquid to solid and back again. And that's
Wow.
key.
Mm.
And that's really critical, because if it doesn't take a ton of temperature to difference or rise or fall to turn ice from solid to liquid and back again, that means the ice at the poles can go with temperature change on the planet through a relatively narrow window. It can go from solid to liquid and back again, and that affects the entire planet. So the fact that ice is hot it really relates to what what temperature it will melt at and how that compares to the ambient temperature. So it's pretty remarkable. So ice is always at a knife edge between solid and liquid. Doesn't take a whole lot of change to the planet to flip from one state to the other. Now you can say, who cares, right? Why? Why bother? Well, you really bother a lot, because the polar areas are about 8% of the surface area of the Earth, but they hold about 70% of the fresh water of the planet. They're our bank, our vault of fresh water. So when that ice, if you have a small amount of temperature change that can turn ice from solid to liquid water, then that can affect everything. It changes sea levels, can change a lot of things, a lot of important properties of our planet.
You also mentioned blue ice and the crevices found in Antarctica. Tell us about this. Well, first, what it is and what it's like, but getting to it and finding it. What is that like with the blue ice?
Oh man! And so ice on the surface is typically white, but the oldest and densest ice looks blue. And people, if you've flown over icebergs or taken a boat and seen icebergs, sometimes you'll see a bluish tint to the ice, and that's because of the absorption of the ice, of the light of ice, and what it reflects and so forth. And so you see blue when it gets dense, when it gets really dense.
In Iceland, I've seen this, I believe. Yes, because I've been to some glaciers there.
It's incredible. It's so beautiful. I mean, honestly, when you see ice, so we're so used to thinking about ice like as a, something in our drinks or something you might slip on in winter in certain parts of the country.
Yeah.
Nothing like that. When you have ice the size of a continent or a state or whatever, it's like all bets are off. So the colors are amazing. So you can have this deep blue when you get the dense ice. So think about the ice. You have snow falling, right? Every year. So some years the snow stays, and then the ice gets, more snow falls with each passing year, the ice below gets more compacted and denser and denser and denser. Well, imagine that compaction happening over 10,000 years, 50,000 years. All of a sudden, the ice at great depth gets super dense, really hard. And so that's the blue ice, typically. That's really hard, really ancient. And if I was to pull it up, you could barely crack it with a rock hammer. And you really can't get, when you have a slope of blue ice, when it gets pushed to the surface, you can't really walk on it very easily at all. You can slide for a long period of time. It's frictionless. It's crazy. So the oldest ice is extremely dense. It's blue ice. It forms at depth. So remember I told you we have miles of ice there, right? It forms at depth. With each passing year, it gets more compacted. There's movement of the ice. Often it pushes it to the surface, so you'll actually see it at the surface. Now, one of the things about the ice is when you're working on it, you have to be very mindful of cracks, of crevasses. And these are cracks that could be hundreds of feet deep. They'll eat a snowmobile with a person on it, so you have to rope up when you go by. And they can be invisible on the surface because you can have snow bridges.
That's the scary part.
That is super scary. And so you always have to be prepared for that. Now you train when you go to South Pole, when you go to work in Antarctica for, like, say, the U.S. Antarctic program. They train you how to pull your colleagues out should they fall into a crevasse. So you walk around with a belt, pulleys, and ropes and so forth. And they'll typically lower a crew member into a small crevasse, and the rest of the crew has to pull them out. But ice is incredible. I mean, it's not just the colors; it's the sounds. Ice makes crazy sounds. It could, when it cracks, it makes a boom like thunder. When it's just moving gently, it sounds like sizzling bacon on a skillet. It's crazy. It can be very disorienting encountering polar ice for the first time.
I guess sort of similar or connected. You talk about how there are lakes underneath
Oh,
the Antarctic ice sheet, which again, maybe maybe that's not too hard to realize. But I mean, there's entire lakes. One example you give is Lake Vostok that's there. I mean, what information can we glean, or have we kind of gained from studying this blue ice that's very deep and very dense, and from other lakes as well that are on the Antarctic? What kind of information have we been able to get from them?
well, I mean, there's all kinds of surprises in the ice,
I'm sure.
and one of the biggest ones is scientists or natural philosophers about 120 years ago looked at the surface of the ice, thought about the properties of ice, at the level of like thick ice like you have in Antarctica, and made the prediction that maybe there are lakes underneath the ice of Antarctica. Freshwater lakes, just actual water, liquid water. And then a series of crews, mostly Russian, out of Vostok Station, did a drilling project where they drilled almost 2.5 miles into the ice and then found beneath the ice a large subglacial freshwater lake with actual water that's about the size of Lake Ontario in the Great Lakes.
That's wild.
It has islands in it. It's a whole hidden lake underneath the ice. And then when they pulled samples up, not from the water itself, they did it from the ice on top of the lake. They and then some American teams from Montana sampled the waters that came up from that. It turns out there's life inside, microbes. There are all kinds of different microbes, and some of the microbes maybe even inhabit the guts of fish, so who knows what's down there. So there's a whole ecosystem of microbes that lies under the ice, miles under the ice, in a freshwater lake. Now, you could say, is this a one-off? Is there only one lake? No. Turns out there's satellite imagery that can capture the lakes under the ice. And it turns out, when we analyze the ice from satellites, it turns out there are about 600 of these lakes under the ice, some of them the size of some of the Great Lakes. So you have whole hidden worlds that have been separated from the surface for millennia to millions of years, with life inside them, whole ecosystems that have been evolving separately from the surface for millennia. They're living without sunlight, so they're getting energy from breaking down the chemical bonds of some of the molecules down there, the compounds down there. And there are whole ecosystems that have arisen around those. So this really shows kind of the extremes that life can go, that life can live in. It provides a model for maybe thinking about how life might have evolved in some of the icy moons of our solar system, whether it's Saturn's Enceladus or Jupiter's Europa. And it also shows just how much we have to learn about our world, that we have these huge lakes underneath the ice, whole networks of lakes underneath, with rivers connecting them, whole hidden world.
I mean, it's a marvel to think about. I mean, what is the possibility or likelihood that there are species of animals that have lived down there for thousands or longer years, if it's been untouched by humans and other types of animals? Like, is it possible that we have really maybe the oldest living animals that have been kind of untouched, or what evolution looks like down there? I mean,
I don't think it's impossible at all that there are some. I don't think it's impossible at all that there are multicellular creatures down there, because what one of the things we haven't found them. I mean, there's potential for tardigrades, these small, the highly durable, microscopic one,
right,
incredibly cute.
Mm-hmm.
And there's again the suggestion that maybe if you look at some of the bacteria, some of them do inhabit that they found. They do inhabit the guts of fish, so maybe there are fish down there. I don't know. But I mean, it's not inconceivable, because the one thing you learn about studying polar regions, and it's one of the stories I really loved to tell in the book, was just to the extent animals and microbes and life can evolve to extreme conditions. That these are conditions where on the surface you say, there's no way life can survive, but the reality is life finds a way, right? And it does so with different kinds of metabolisms. It does so with different kinds of inventions, which allow creatures to survive in these wild places. So, no, I mean, I think, this underscores just how much we have to discover about our own planet, and how the more you look, the more you learn that something that seems so simple, i.e. ice, is really amazingly complicated amazingly complex, and we're dependent on the complexity of that incredible substance, So,
How does discovering many lakes and maybe rivers connected to all these things, how much does that influence or impact what we know at the surface with like the Southern Ocean, say, right? So how much do you feel? Granted, you're saying 2 miles deep, within a continent, but obviously things aren't, completely an island. Everything's connected. How much does maybe the surface or the Southern Ocean that goes around Antarctica potentially? I mean, maybe it's hard to know at this point, but impact some of the things that are going on the continent.
oh, huge. I mean, honestly, the impact of the Southern Ocean, if we're just looking at Antarctica right now,
Mhm, mhm,
the impact of the ocean around Antarctica has dramatic consequences on the ice.
mhm,
So, satellites are always looking at the ice of Antarctica from the space. And you can
mhm,
see some of these we can get with lasers shooting down and pinging back and forth from the ice back to the satellites and other amazing technologies, which I describe a little bit in the book.
mhm,
What you have are a 24-hour view of what's happening to the ice. How is it changing? How is it
mhm,
changing in mass? How's it moving? How's it changing in height? So we really know these things very well from the satellites in space. And one thing you can see is the ice is always moving,
mhm,
and the ice is melting in certain particular ways. That is,
mhm,
most of the melt of the ice does not happen in the center of Antarctica. In fact, if
mhm,
anything, in places it's growing there.
uh,
So it's not melting as much from top down.
mm,
Where most of the melt is happening is at the coast, at the margin, where the
mm,
ice along the coast meets the warm ocean waters.
mm,
And it's that connection between the warm ocean waters and the glaciers along the coast. Those waters can seep underneath the glaciers there, and
mm,
they melt them typically from below. So
uh,
that's where most of the melting is happening, at that interface between ocean water and ice. Now, the ice is moving from the center of Antarctica. Think of them as ice rivers, if you will. They're called ice streams. They move like as rivers.
mm,
The ice can move about 1.5 kilometers a year, almost a mile a year,
wow,
really fast from the center to the margin. And it's being held back by from going into the ocean by these glaciers along the coast. But they're
mm,
the ones that are melting, with the rising
yeah,
temperatures of the ocean. So as you lose those dams, we're expecting more ice to enter the ocean. How much is anybody's guess?
oh wow, yeah. It's I've done some reading on the Southern Ocean. It's very 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 important. Obviously, I mean all oceans are, but and granted, it's really all one ocean. But as we kind of market it, in that way, it becomes really important for conservation and many other things. You talk about many other really cool things in the book. You talk about natural antifreeze. I'm curious about this. Arctic
Yeah.
willows, insulation in polar bears. Really, this idea of, I mean, I think what everyone's probably wondering is, well, how do organisms survive in whether it's the Arctic and the North Pole or Antarctica? How has evolution, helped them to survive in such, really really tough conditions?
One of the coolest things about studying the polar regions is learning how creatures have evolved to survive there. And they have all kinds of really cool tricks. One of the tricks that you brought up is a number of creatures have a very specialized protein, or different kinds of specialized protein, which serve as antifreeze in their bodies, in their blood, and their cells and tissues. And so they've evolved these antifreeze proteins, which can slow down the formation of ice crystals. They're natural
Mm,
biological proteins that
so
serve as
cool.
antifreeze that can slow down the formation of ice in the body, or they can slow down the damage of the ice, the relationship to the cells, and how they cause damage to them.
Mm,
So you have these, and this has happened multiple times, evolved multiple times independently. In some cases, you have the creatures have evolved this by modifying a few liver enzymes to gain antifreeze properties.
mm,
Really, really, really incredible. One of the antifreeze, well, one example of this is like gets even crazier. That is, you have some roundworms, worms that live in conditions where it can dry out for long periods of time in Antarctica and then kind of get wet again. So, but to survive these droughts, what they do is they replace all the water in their bodies with a sugar known as trehalose. Other creatures do this too. And when they do that, they turn into glass, clear glass. You can shatter them. And they stay as glass in the suspended animation for a period of time until it rains again or snows again or whatever. And then they reanimate. So all these cool tricks to survive in these incredible landscapes. And, love telling the stories of these. One of my absolute favorite polar animal. It's not a polar bear. It's not a penguin. It's the Arctic woolly bear caterpillar. It's a little caterpillar. We have a version of it down here, which is a hairy caterpillar, lots of hair. And what it does is when in the summer in the polar region, say in Greenland or Ellesmere Island or those areas, in the summer, what it'll do is it's daylight 24 hours a day. And so it'll sit and absorb the radiation from the sun and get warm. And it has the fur on the outside of the body, this caterpillar's fur, which will keep the heat inside. So it'll basically, and then stay warm, and then it'll eat voraciously. It'll eat whatever moss and leaves it can find. And it'll eat voraciously for 4 to 6 weeks. And then when the conditions start getting dark and cold, it will freeze over for 7-8 months, having an antifreeze protein in its body so it doesn't damage the cell, but it'll essentially freeze over. And then it'll thaw out again the next year, feed voraciously, store the energy, freeze again, feed voraciously the next year, freeze again. And it'll do this freeze, feed, all storing energy the whole time for 7 years until the 8th year, it'll metamorphose into a moth, fly for a week or two, reproduce, and die. So it's like 7 years of freeze thaw, all for the purpose of a couple weeks of flying and reproducing. And each of those years is storing energy. Amazing animal. So the way it does it, it has this checklist of polar adaptations. It has the hair, it has antifreeze protein, it has behavioral cycles which allow it to modify its behavior relative to what's happening outside of the world. An amazing little animal. It's this big. I mean, you set up camp there, you might look down and you might have an 7-year-old caterpillar at your feet. So you got to be careful where you step. You don't want to something like that. It's a second grader.
Wow, that's so wild. That is so wild. Wow, that's incredible to
right.
That.
I mean, and so it's like, so I was like living with this, living in these regions, seeing these creatures and doing the science there and meeting the scientists is like, this book I've been working on this book for, I would say, since I stepped foot on the Arctic for the first time since 1988. So.
Wow. And you also mentioned in the book the Inuit communities as well. They live up in, I guess it's the Arctic Circle, right? I mean, in different parts of the Arctic Circle.
East Greenland, West Greenland, throughout what's called Nunavut territory in Canada, northern Quebec, parts of Alaska. Okay. Yeah, exactly. Siberia. Yeah, so there's whole communities that are up there.
They're Homo sapiens, they're humans, right? They're us, right? Definitely. And so how, you're talking about, these, you've talked about, caterpillar and then, some organisms and polar bears, but for humans, how have humans, and this is, one group of humans that has learned how to survive in these conditions, how have they, kind of learned, how are things different, I guess, in their community for how they kind of live every day?
Well, I mean, humans are an amazingly adaptable species, right? We have human populations that live in high altitude.
Yeah.
We have human populations that live in deserts. We have human populations that live all over the world. And in each place, we adapt as a species. So the way our species has adapted to the northern polar regions is in a lot of ways there are biological properties that they have in terms of some of their genes and the way they are able to metabolize fats that might be different from people whose history is in more southern regions, from populations where people are more southern regions. They have behavioral adaptations as well. I mean, I think, when you work up there, you encounter an Inuit code of behavior, which when you write your application, when you do your interactions, you're guided by this code of behavior, which forms a social glue and expectations for people and how they behave and how they will interact with the landscape and the environment. Respect for the landscape, respect for elders, working together towards a community. So there are, no person's an island up there. It takes a village to survive. And so what you have are cultural practices which have allowed them to survive in these incredibly challenging conditions. They're not challenging for them. They're challenging for us. Obviously, if I was up there like winter for, where it's dark for 6 months. That would be challenging, but they have a whole series of practices that enable them to thrive in these areas. And I got to say, the European explorers who did best working up there were the ones who really took lessons from Inuit practices and communities and their way of life to enable them to work up there.
Mm. Now, you're famous for working with a team of researchers to find the all important or discover the all important Tiktaalik. Am I saying this right?
Mm-hmm. Tiktaalik, Brazil, yeah.
And which for listeners was technically it's a intermediary species between fish and land mammals. Is that right? Is that accurate to say?
Yeah, you can see the plushie right behind me. Right?
Yeah. It's and so it's very, very helpful.
Be real.
Yeah, it has to be right. And this was in the Devonian period. Which period was it again?
It's in the middle to late Devonian period. Rock's about 375, 380 million years old. They're from Ellesmere Island in Canada, which is Canada's northernmost island.
So super important, big discovery there. Have you felt sort of maybe in some ways kind of the hangover? It's like, when am I going to find the next big important fossil? I mean, they're all important in different ways, but when going to Antarctica, you talk about in the book a fossil plant, Glossopetris, which also lived 300 million years ago, being discovered there. You've been going to Antarctica and the Arctic for a long time. What other types of fossils, I guess in Antarctica is what I'm very curious about, because we don't hear about as much, have you discovered? Maybe not, intermediary species, but other things like that are really, really important to be like, wow, we've never seen this, or wow, this is the first, or this tells us a lot about this period. What other, I guess, big fossil discoveries have you had?
Well, yeah. So, I mean, look, the minute we found Tiktaalik, we were like, okay, where are we going to go next? I mean, it was like, right. Science is a never-ending quest. I mean, it's like, and when you think about things as like, when you kind of know how to look, the whole world becomes a treasure hunt, right? Depending, sure. You kind of learn the rocks at different places. Mm-hmm. So the thing that drew us to Antarctica were those mountaintops in the Transantarctic Mountains, and a particular part of the Transantarctic Mountains, a place called Victoria Land. About 200 miles out of McMurdo Station, which is a scientific station run by the U.S. Antarctic Program. Those were formed in ancient rivers and streams, much like the North, only a little older. And we were able, so the Devonian is also known as the age of fish, because it's not just the time period that contains the fossils that tell us about the transition from life in water to life on land. It also, at different parts of the Devonian, tells us about the early evolution of pretty much every major group of fish. Sharks, rayfin fish, lobefin fish, all these other groups. And so that's what we're there to do. We were really kind of understand the world and gain a snapshot of what the world looked like back in 380 or so million years ago. Get a different window onto it than what we had up north, where we discovered Tiktaalik. We found some freshwater sharks. There are sharks there that live in freshwater in the Devonian of Antarctica. You don't want to swim in those streams. So just note to self. And all kinds of armored fish, fish with body armor, that are some of the earliest fish with actual jaws. And then some fish that are closely related to you and I, that are cousins of Tiktaalik and cousins of you and I, a little deeper in the tree. But no, it's a real aquarium, if you will, of early fish. At the tops, think about it, it's an aquarium inside the rocks in the tops of mountains of Antarctica. So there's an image for you.
Yeah, that's that whole idea of the world as a treasure hunt it has to kind of to feel that way. I know I've talked on the podcast with Steve Brusati, who obviously is the, I guess, dinosaur man of sorts, of course, but he's also talked about like when you find things. He goes up in Scotland and stuff. And
I know. Well, Steve was a student here at UChicago. He was an undergrad here, so
he's great.
One of our students here.
He also talks about it sort of in the same way of like this whole like you find one, you find all, you want to keep going, you want to keep finding all these things.
Oh, definitely. No, that's definitely the spirit.
Yeah. So I guess one other thing is really curious thing is I wasn't expecting to find it in the book was this idea of meteorites landing in Antarctica.
Yeah.
And you talk about aluminum 26. Why are they attracted to Antarctica? What is it about the ice? Maybe tell that part of the book. That story was like really fascinating as well. It's like I did not think about that. Tell us about that.
So I wanted to tell the story of like how we study life, the cosmos, and our future. And part of the cosmos, in studying the cosmos in polar regions, is we have pieces of outer space coming to Earth that we collect for free, more or less, right? We don't have to launch missions to Mars. They land here. Right. And so the thing is, to understand meteorites in Antarctica, it begins by understanding the movement of ice. So meteorites and cosmic dust and all that good stuff, they're always hitting the Earth. Not often, but rarely, but they do hit the planet. And what happens is the ice in Antarctica is always moving like a conveyor belt. It's always moving like a conveyor belt from the center of the continent to the coast. We talked about that a little earlier. Now, what happens is when that conveyor belt hits a mountain range that pokes through the ice, it backs up like the conveyor belt that held the pies that Lucille Ball was making. And they all pile up at the base of the mountain, right?
Right.
Now, and what you have is some of that old ice, the blue ice that gets pushed up as part of that mishmash that happens at the base of these mountains. So you get all old ice churned to the top is this big pile at the base. The conveyor belt just keeps on bringing it. So it gets this pile up there. Now, everything that was in that old ice starts piling up at the base of these mountains, at that pile up where the conveyor belt hits the mountain. And some of that includes meteorites. So meteorites hit the Earth pretty much everywhere at the same rate. But what happens in Antarctica is you'll have places that collect every meteorite that's hit there for the last 120,000 years or 200,000 years. So if you know where to look in Antarctica and you know how the ice moves, you can choose which mountain to go to, which blue ice to look at. So you're looking at the old blue ice because it's all coming out of the blue ice. And you'll find piles of meteorites. And so the US and the Japanese and some other countries, the Belgians, have run meteorite hunting surveys. And about 50,000 meteorites have been discovered in Antarctica since they started looking in the last 4 days. It's enormous. And some of these meteorites are pieces of Mars that broke off during an asteroid impact and hit the Earth. And we can date how long they've been on the Earth by what you mentioned is aluminum 26. Because when a meteorite hits the Earth, it no longer is affected by cosmic rays. And the cosmic rays actually, when they're in space, cause some of the molecules to produce some of the atoms to produce aluminum 26. And that process stops when the meteorite hits the Earth. So you can actually date how long a meteorite has been on Earth by looking at aluminum 26 and other atoms. So you can tell that some of these meteorites hit the Earth 100,000 years ago. And it's through motions of the ice that they started to pile up at the base of these mountains. And so expeditions are run every summer by the U.S. Antarctic program to collect meteorites, because it's a cheaper way of getting pieces of the moon and the early solar system and Mars and so forth and asteroids. They just drop on. They're always raining down to Earth. They do so infrequently, but if you know where to look in Antarctica, you can find collections of them. That's kind of that's amazing. I didn't realize that until I went there.
I didn't realize. I was reading it. I was like, wow, that's remarkable.
Yeah, and they do the same thing with cosmic dust. So cosmic dust is raining down everywhere too. And there's this machine called the Cosmic Dust Sucker, which is at the South Pole. And the South Pole is known for having the cleanest air on the planet. And so what it does is it's sucking the air in. It has these filters, and it's filtering out cosmic dust. And it has no soot or any of the other stuff that we have up here. So they can actually get particles of the early solar system that rain down and collect them at the South Pole.
One thing here, I wanted to ask it earlier, but it really is a kind of global thing. There's the you mentioned in the book briefly the Antarctic Treaty in 1959, and you said there's 70 scientific bases from over 29 countries in Antarctica. McMurdo Station is kind of the central place. When I was reading about McMurdo Station, I was trying not to think of the thing.
Good luck with that. They show that movie like 4 nights a week.
Oh my God, I could not watch that movie if I was there. Oh man, I'm 500 miles away from the last human. Oh my goodness. Yeah. So I mean, does it kind of feel like like a United Nations down there? Like, you're hearing Spanish, you're hearing English, you're hearing French, you're hearing German, you're
Oh
hearing
yeah.
Arabic.
Oh, it's
Is it
amazing.
kind of like that?
Well, you feel how international science is because countries have to work together to do the big science there. The Americans and the Russians had to work together in
Yeah.
the Vostok core. The British Antarctic Survey and the U.S. Antarctic Program had to work together to understand some of these glaciers that are melting in West Antarctica. So you really do feel that. It feels like the cantina scene in Star Wars, where
That's
each
cool.
country has its. If McMurdo seems to be a base where a lot of other countries initially set down, and then they'll go their own way. And so you really do feel the international flavor. The teams I ran were international. We had Australians, we had Icelandic, we had a lot of we had a number of different nations. Americans, of course, is part of that.
Mm. Eh, And now you don't. There's no towns or cities over there. Obviously, it's just scientists, right? That nobody
Yeah, yeah.
really
On the
lives there.
continent itself. Now you have
Yeah.
as you go towards Chile and get some of the islands, the
Sure.
southern islands, there are towns there. But when you go to the main block of Antarctica, the main continent of Antarctica,
Hmm.
there's an Antarctic treaty which says that no nation can have set up military operations there. No nation can
Mm.
set up mining or extraction there.
Nice.
It's really only for science and in some
Nice.
cases tourism.
Uh-huh.
But that's kind of it.
Yeah.
And it's amazing because there's no permanent human settlement there. These scientific stations, people come and go. You
Wow.
might have people there for 8 months or a year, but nothing longer than that. So there's no permanent human settlement. And I think the maximum population size of the continent is at any given time is 4,000 is the
Wow.
maximum during the year. And
Wow.
that's in the Antarctic summer. So it's not inhabited by people. There's no indigenous population there.
Hmm. Hmm.
It's international territory.
Yeah, that's pretty cool, actually. Obviously, climate change is, I mean, I feel like I've been talking about climate change my whole life, and so unfortunately, we as a human species, we have not done enough to rectify some of the ways we've kind of destroyed the planet. But I do worry about climate change. Obviously for the planet, but also certain parts of the planet more than others. I mean, how much um, has climate change really affected, maybe negatively, Antarctica and the North Pole? I mean, there are legitimate worries and concerns still that increase over every year. No.
Yeah, and so this is not theory. This is objective measurement. So we can measure what's happening to the ice. Remember, I told you
Yeah.
about those satellites that are always looking down at
Hmm.
the ice of
Hmm.
Greenland and always looking down at the ice of Antarctica. There is no doubt that we're losing about 280 gigatons of ice per year from Antarctica and about the same number, maybe a little bit more, from Greenland.
Mm.
That's up from about 40 gigatons per year, 40 to 50 gigatons per year 20 years ago in Antarctica, and about the same in Greenland. So the amount of ice we're losing has accelerated over time, and it's actually at large levels. The other piece of this that's really big is, remember I told you where most of the ice seems to be melting is at the coast in
Hmm.
Antarctica, where
Hmm.
that Southern Ocean, the warm waters of the Southern Ocean meet the coastal glaciers. There has been a lot of work looking at what's going on in those glaciers, particularly in West Antarctica. And they've been looking at those glaciers, and they've seen those glaciers have been retreating very fast. They're getting thinner. And the problem is when those glaciers go, they're the ones that are holding back lots of ice from the interior of the continent from entering the ocean. So we're losing the dams that are holding the ice back from entering the ocean. Now, the challenge with this is actually to make predictions. So I can tell you right now what's going on.
Hmm.
It's very clear we're losing ice. It's very clear we're losing ice in very critical places. But what's the future? What's 5, 10, 15, 100 years, 200 years? What it'll look like? And it's hard to make those predictions with any great confidence. It's very clear we're going to have sea level rise. There's no doubt about that. The question is how much?
Hmm.
And and there you run into different models that have different assumptions and different things built into them that give us a range of the amount that sea level rise. There are some models that have about 10 feet of sea level rise in the next century and a half. Others that's significantly less, on the order of half a foot, something like that, which is still a lot. but it's not, dire like that. So, so that's kind of where we're at. We can document this very well. And now what we need to do is this complex substance, ice, we really need to understand it much better to make really robust predictions about what's likely to happen to sea level, to ice, and then ultimately sea levels to our planet over, the coming decades or centuries.
I guess the quick follow up to that someone listening could be like, well, okay, Neil, yeah, it's fine, ice, okay, that's not great, but why do I care about ice? Like, why do I care if Greenland and all these, gigatons of ice, in Antarctica and Greenland, the Arctic, like who? All right, we have ice and then we don't have ice. Why should people care about losing that much ice? There's the dam analogy, but why else?
Yeah, so if you look at, sea level, we're really dependent on sea level in a very big way. So the coastline of different countries, the cities that lie along the coast of different countries, the cities that lie below sea level. So, with a rising ocean, you lose Pacific Island nations. They'll disappear because they're just barely above sea level. We'll lose coastal real estate. We'll lose cities such as New Orleans and Miami and, other places in part of Bangladesh and so forth that can be gone. But importantly also, it affects everybody, whether you're not at the coast, and that, when you have all this fresh water entering the oceans, it changes ocean currents. And ocean currents are big movers of heat across our globe. So when you do that, you're changing global weather patterns, which can affect agriculture, can affect many of the things we as populations who live closer to the equator really depend on. And so, we take for granted that much of our world really depends on certain weather patterns, certain sea level patterns, in really profound ways. And as they change, we as a species are going to find ourselves having to adapt, sometimes probably very quickly.
Yeah, so it's a lot there. Last question is, where do you see is the future for I guess researchers in polar science and the North Pole and Antarctica? I mean, Antarctica sort of feels like Earth's last frontier in some ways. It feels like this we're still, discovering all these things. I mean, when you think about obviously your life's work and what you've been doing and what you're continuing to do, but you see a whole other generation of folks that are going to do this type of science. What kind of still gets you excited? Where like, we could find this, we could find this. Here's the thing that we could do here. Like, what are those things that kind of excite you with polar science?
Well, people like me are always excited about understanding our past and how our world was made. And there's so much to still discover about the history of life. And much of that exists likely in the rocks of Antarctica, Greenland, Canada's Ellesmere Island, and Russia's Siberian North. And so forth. So there's so much still to discover about the past, but importantly and urgently, there's so much we need to understand about our future. That's the key thing. And that's embedded in the ice of the poles. And I think ice is so complicated, and ice behaves in very important ways. We've already talked about how the condition of the ice in Antarctica and Greenland really is essential for understanding our own condition. But what we need to do, the next frontier, is really to get better predictions and better understanding of ice so we can kind of know what our world is going to look like in 15, 20, 30 years.
Absolutely.
And beyond.
Neil, as always, you're such a great scientist, great communicator. It's always a blast having you come on. You're always welcome to come on. I greatly thank you for time, energy, wisdom, and people should go get your book. And I'm looking forward to all the other things you discover and find about our past and our future on the planet.
Well, thanks for having me. Appreciate it.
Absolutely.